the plan is to discuss the last thing that one has to check in order to apply Lieblich-Olsson deformation technique, and then we go to application. So, okay, so the setting setting, we have A0, Euclidean, W algebras, and they are like in an infinitesimal extension like that. I squared from 0. We have x and y smooth projecting over k equal to y. And then we have x0, a deformation of x over a0, y0, a deformation of x of y over a0, and then we have ya, a deformation of y over a. We have that x and y are related by derived equivalence. And we are already in the step in which we have lifted these at the A0 level. So we have a map between x. We have an embedding into S. It should be early. The y0 over a0, and so this lies over. So this is x0, like here, and here we have this over a. So in order to run the deformation argument, we need to check that let's call this composition here, okay, kappa, that the image of kappa lies in the smooth locus of S D Y A. And this amount to check the smooth locus of this over A. So this, since the smooth locus is open, it's really enough to check it with A0 equal K. So and the condition we get is again from deformation theory. So there is an element. So here we will have, we get what we really have to check is that for every x rational point over k, so px, so we have, okay, so we have px is p restricted to x times y, and we can consider this space. Well, this space is the obstruction space for this moduli problem. So in here we have an element and we want this to be 0. So again, deformation theorem. Okay, so how do we prove that a perfect complex is unobstructed? So there is a theorem that in this full generality, it's 2020 from Lieblich, so it's after what we did, but so it's another paper by Lieblich and Olsson. I remember that I received an email 2 days after my daughter was born by Martin saying, "Hey, we approved this. Can you read it?" And I say, "Well, it's interesting, but my daughter Astrid is just born. I don't think I will be able to do it for like at least 3 months." And Martin replied, "Oh, also my daughter's name is Astrid." So, okay, so it's I think will always be impressed in my life because yes, it's yeah, I should have simply disinstalled my work email from my phone at that time. But okay, so anyway, so that is why I know the year of at least the preprint was out. I don't know when it has been published, but okay. So if you have x over step A, flat arcing stack with omega x over A medial, and P0 a perfect complex on x, then and determinant of P0 I call L0. Then we have a trace map from x to P0 tensor I into x. It's injected in O tensor I. And this map send the obstruction of P0 into the obstruction of the determinant. So it's enough to check that the determinant is unobstructed to see that the perfect complex is unobstructed. Okay, so now application. I'm almost like a pro now. Should have another week of lecture and then. Okay, so application. So finally. So one is the derived. So this is a theorem. This is Lieblich-Olsson. So you have x, y, K3 surfaces. Actually, you don't need to assume that y is a K3 surface. It will be a K3 surface. It is a K3 surface. K3 surface as soon as I say that there is a derived equivalence between x and y, that I will abuse notation. In cohomology, we send the Chern character of a skyscraper sheaf in a Chern character of the skyscraper sheaf, then x is isomorphic to y.
What's the base for it?
It's k over k bar, char k, different from 2.
And I think actually you can do car k equals 2. They just didn't have this result of the Tate conjecture, like Curti-Mata-Quisi-Pera.
Yeah, no, it's. I don't know. So it's.
I talked more about
already.
this.
It was already known at that paper.
Oh really?
Yes, because they use it. Like in the
never mind.
second version of the paper, they use it to see that because Tate super singular is super singular.
Right.
So they simplify the argument for finite height.
But they still can't get around Carnot. Okay, that's okay.
So yeah, so I think it's still true.
I'm the only person who cares specifically about car k equals 2.
Yeah.
That's my problem.
2 is even, cannot be a prime. Do you know prime?
Yes, I know.
Do you know even prime numbers?
It's not even a prime number.
Okay.
It's not a prime number.
Okay, so consequences. I hope they want to watch this on YouTube, but sense of humor.
Hi.
Okay, so
Okay.
anyways, so the consequence of these are many. So one is Fourier-Mukai partners of K3s are modular space of sheaves. Exactly the same proof that I gave for abelian surfaces. And then two, if so it's K3 who have a lift with no FM partner, no a lift, let's say a good lift, because I will have no FM partner. And so this is will tell you that as a consequence of this, they have a super singular, like rho of x greater or equal to 12. The Picard then no trivial FM partner. So for finite height, like it's your modular space of sheaves, same argument. Finite height, you have a lift that preserve the Picard, all the Picard group, and so in particular you get that in that case, if you have always finitely many because it preserves everything, and so it means that every Fourier-Mukai partner is a specialization of a Fourier-Mukai partner of the lift. And this good lift is a lift in which it lifts the line bundle of the Mukai vector. And after these and all the stacking thing I did last time, the other technical heart of the paper is that for basically Max and Martin are able to produce a particular lift given a Picard lattice. They produce a particular lift in which the L of the Mukai vector lift, and the particular lift as a Picard lattice is this hold that the Picard lattice is made in a certain way that it has just one, the complex one has just one Fourier-Mukai partner. And this is why, so it's really, again, you have this really powerful tool, and then everything is producing nice deformation of X. Okay, so let's see how this is proven. So step one, before going to step one, let me know. So I want to use that theorem. So obstruction for trivial canonical bundle, which K3 have, obstruction to lift perfect complex are the same as lifting line bundle. Of course, there is the bad news is that on K3 you cannot lift all line bundles. You have to be careful, but you sure can lift all. So the obstruction to lift the perfect complex here vanish.
So the one is to reduce the characteristic zero, right? Characteristic zero
yes,
is known.
Yes, characteristic zero is known. It's due to Bridgeland and Machocha. So that is, so the characteristic zero is known. It's due to Bridgeland and Machocha.
Oh, the specific version that specifies this particular vector.
Yeah. And so the step one, so step one is, so the other problem is now, is if you remember, so, okay, I have no obstruction to lift the perfect complex, so I'm fine, but I have to algebraize. So I deform y, like I find a projected lift of y, I find a formal lift of xn where the perfect complex lift, and I have to algebraize it. But the step one is, I can assume, so I look where f of 110 goes. So f of 110 is of the form 1b squared over 2. It's because I used the Mukai pairing, and I have that. So f of 100, so this is O, is R, L, right? For some class in the non-severe group, and then I have that 1 is R, L, chi against the image of 0, 0, 1, which is 0, 0, 1. 0, 0, 1. And this is exactly R. So R is 1. Then this is isotropic. So also this has to be isotropic. And so I have that 1 L chi square is 0. And this tells you that chi square is equal L square. Okay, so this is of this form, which means that step 2.
Because the chi is no square, there's no chi square.
Yes, yeah, chi is, it's 2 chi is equal L squared. So step 2, I have this. Well, B will be some class or some line bundle, and then I create another equivalence that is L minus 1 tensor phi. That, let me call it again phi. It's up to twisting phi for the tensor product of a line bundle. I can assume, so this equivalence send 1, 0, 0 into 1, 0, 0. If you do, so if you twist phi the class of, you can check, like, you check out twisting by, tensoring by a line bundle, then it is like that. Okay, so you can assume, so if there are derived equivalents, you can assume that you can assume that 0, 0, 1 goes into 0, 0, 1, and 1, 0, 0 goes to 1, 0, 0. And so, since the neuron severity of X is the intersection of the orthogonal of 1, 0, 0 and 0, 0, 1, you can assume that phi takes line bundles into line bundles. And as a consequence of result of August, by twisting with spherical twist, you can assume that amp X, the ample cone, goes into the ample cone. And now we are done because we have Y over R, and we have a lift of an ample line bundle over Y. And at every step, so we have Ln in, so here I'm putting something under the rug, so at every step we have Ln a line bundle of 1 Yn over Rn, which come from, so ample, from a Nn over Xn over Rn. So I use these to see that it's just when I deform the equivalence, I can bring with me an ample line bundle on the X side. So the formal lift of X is actually a projective lift of X. And then the Grothendieck existence theorem for perfect complex, everything algebraized, and we have an equivalence up to like phase change to see. So see that this is like we have two lifts with the derived equivalent geometric fiber, and what's happened is that 001 we go into 001 also in the geometric fiber, in the generic fiber. So let's write it down. So we got Y over R, X over R projective, and an element here such that P pi eta from D B X eta to D Y eta is an equivalence, and this sends 001 into 001. It's like invariance of polynomial. And then you're done, no? Because now over C this is known by Bridgen and Machocha, and so we are done. So okay, so application 2.
Where we use characteristic not built here.
I have no idea.
It looks very formal, right? So.
I know. I have no. They never pointed in the paper, so I have no idea where.
Yeah. Like I asked Martin in the summer, he said, "Oh, I don't think we need it, but we just were lazy, basically."
Yes, it's so in the other paper they were using not two,
Yeah.
and actually there was a little problem in characteristic 3, but then they were fixing with another deformation. So yeah.
So the spherical twist sounds like a problem. Spherical twist is a subtle thing.
Yeah, so I have no idea. Like I can tell you where we use characteristics different from 2 and 3 in the second application.
Okay. Yeah, I agree. I've read the paper and I couldn't pinpoint exactly where they needed either.
But in the paper, for example, they were not even discussing about obstruction of perfect complexes and the fact that you need omega. The fact that So when I was reading the paper, I was not really understanding where in this deformation of P they were using that is a K3 surface.
Yeah.
But they were subtly using the OX is trivial here because of the obstruction thing. Okay.
Sorry, can I ask a question? Like phi, I can see why phi takes the class of line bundle to class of line bundle. Why it takes line bundle actually?
I think you can do it in, like you have a 1L, like you have the Chern character, the Mukai vector of a line bundle. We end up in the Mukai vector of a line bundle, and I think it's okay. But yeah, it's yeah. I don't really remember that part. So, and I didn't review because I didn't have time to present it. So this is why it's yeah. Okay, so let's go with Enriquez and Lieblich.
Sorry, but this derived really, can you make it better? Just like in terms of some.
Yes, in the second paper they do. So they can show that. So this is equivalence is called filter. There is if you add an equivalent something to it, you can make it a stronger filter. That I don't remember what it means.
But is there such thing as derived equivalence, the same as some homological equivalence?
So yeah, so the thing is, if you add a condition here, then you really produce an isomorphism.
But that's not the usual derived really. It's like not the derived equivalence, same as the Hodge isometry. There's no such thing.
No, it's not such a thing. But so in the second paper, basically they consider this stronger filter. So here they prove isomorphism. In that, they provide an isomorphism that act in cohomology as a strongly. So for any strongly filter, there is a specific isomorphism that act in cohomology as equivalence. And then every filter can be made in a strongly filter by composing with some auto-equivalence. So it's in fact they call that a refined the theorem for. Okay, so Lieblich and Enriquez. And here the characteristic is different from 2, and here the characteristic is different from 2 and 3, simply because these two surfaces are terrible in characteristic 2 or characteristic 2 and 3. So okay, so what the theorem is if X is Enriquez or Lieblich, under the respective hypothesis, then X has no non-trivial Fn function. Okay, so this was known by, Bridgeland and Machocha 1998, over the complex number, Bridgeland and Machocha 1998, with a mistake on the Lieblich that got fixed recently, like a few years ago. Like, there is a new, if you look on the archive, there is a new version of that. And okay, so let's. Yeah, over the complex number. But then if you get over the complex number, by base extending, you get basically any field of algebraically closed field of characteristic 0. So. So let's remind a little. Wait, now I told you it's a David device. You look like a painter. Okay, so Enriquez is characteristic different from 2 as numerically trivial canonical bundle, but omega x is not trivial, and h1 of x is 0. And a elliptic.
Sorry, means square is 0. The first is the square is 0.
Yes, so this is numerically,
Oh, sorry, okay, yeah.
it's numerically trivial but not trivial. So yeah, it's elliptic, same thing. You have that the 12th power is 0, and then there are different types. I'm not going to write the table. And not different, and you have h1 of x or x is the base field, but it's one-dimensional. And these work, this is just characteristic different from 2 and 2 and 3. Otherwise, they're really different. This can be trivial. This can be bigger.
Rational.
Yeah, if you can. Okay, so the good news for both of them is h2 of x or x is 0. And also h2 to the tangent is 0. So they deform projectively, every line bundle deform. So in theory, like it will be not like on the point of view of Lieblich and Olsson, they look nice, but Lieblich and Olsson worked for trivial canonical bundle. We cannot use the deformation, the obstruction of perfect complex goes to the obstruction of the determinant. But there is a way around it. By Bridger and Machocha, another paper, same years more or less. So every one of these has some. Oh well, let's first say Honig's plus Bombier and Mumford, then Fourier-Mukai partners of Enriquez, by Lieblich are Enriquez and by Lieblich. Same argument as for I gave that for abelian surfaces. And then so since the canonical is torsion, you can use a canonical line bundle to create a cover that is equal, because we are in characteristic different from the order of this canonical line bundle. And since this is made, this canonical cover is made using the canonical line bundle, you have Bridger and Machocha. You have an equivalence like that. Lift. So 5. Lift to an equivalence of the canonical covers. but that it commute with the pullback. So let's go this pi. It commutes, everything commute. And so okay, so now we want to use this to, we use this to get around the deformation problem. So what we do is we leave the equivalence here. And the equivalence here, so now here this, so this is either a K3 in the Rickens case or an abelian variety. So in any case, the canonical bundle is trivial, and we could use Lieblich-Olsson. On the other side, these are not, the obstruction of line bundle on the canonical top cover are not obstructed. But what happened is, so what we do, we look at here, and we see that, so there are two things. So we use two theorems. The idea is that we compare the obstruction below with the obstruction above, and the map is injective. So it's enough to choose that the obstruction, to see that the obstruction above is 0 for the perfect complex. Now the obstruction above is 0 is the obstruction of lifting a line bundle is 0. And we show that in this specific case, the line bundle either come from below or come from below tensor something in the peak knot. But the peak knot is as the peak knot of a K3 or an abelian surface is smooth. So the thing is the peak knot is unobstructed, and that it will come from below is unobstructed. So it's so this is the general idea. So
Almost as fast as Daniel.
yes, but Daniel was not covering chalk. Like, I'm literally covering in chalk now, in liquid chalk. Okay. I should hurry. Like, okay, so the first is like that. So we have, we have A0, Y0, and we have a perfect complex over P0. Let me write like that, because here I want to Y hat and Y0 hat, and here I have and this I can get because it's what I said 2 times ago, that I deform it. I deform these and I deform these as a top cover. And so I have YA, which is given, and I have Y hat A, which is given, and well, it's like that. So what I have, so let's put this pi, and I have that the obstruction to the, we have this from X P0 tensor I is injective in X2 of P0 pullback of P0 tensor I, and send O of P0 in O of the lift of P0, the pullback of P0. Okay, but now we use Fourier-Mukai diagram. So let's look with A0 equal K, which then everything works. So let's do with A0 equal K. What happened? So with A0 equal K, well, P0 is the kernel of equivalence times Y, which is exactly the image of a skyscraper sheaf. And okay, but so P star of P0 is P star of the image of a skyscraper sheaf, which by Lieblich-Olsson is phi over P star of a skyscraper sheaf, and which is a direct sum of what's an image of skyscraper sheaf with this should be of skyscraper sheaf here. And since they have all the same, so since skyscraper sheaf have all the same Mukai vector, the Mukai vector of these are all the same, and I can get that the determinant of P upper star of P0 is L0, like is some L0 to the n is how many copies I have, that it could be 2, 4, 6, 3, depending from which Lieblich surface or Enrique surface, like it's the order of the canonical bundle, times alpha, and alpha is in the peak knot of, which of course if this is a K3 there is no alpha because there is no peak knot. This is so the determinant is, and so L0 is the determinant of one of these. So they have all the same determinant up to something in the peak knot, and so the determinant of this direct sum is L0 to the n times something in the peak knot. But now the pullback. So if you look at the map of Néron-Severi given by the P star, the subgroup that you get to is of index n. So these come from below. So this is unobstructed. And this is smooth. So this guy, the alpha, is unobstructed. And so you have that the determinant of, so this is 0, and so this is 0. And so you can run the deformation problem. And since here, like algebraization is not a problem because H2 of OX is 0. So once you have a deformation, the deformation exists. And for so the fact that bielliptic surface have a lift is like Enrique's in characteristic different from Chu. It's easy with cohomology. Bielliptic surface, the tangent is not 0, but there is indices of Pasch that tells you that there is. Okay, so, and then in the last 10 minutes, I want to give you an application that is not a characteristic P. So if you are not a characteristic P person and you survived till now, then I give you this prize. Okay, so this is done by Reinecke, and it used that whatever I said yesterday, modulo some add the technicality word for twisted things. And okay, so now the setting for Reinecke is you have X alpha twisted K3, K3 over the complex numbers. And then, so you can define the twisted Mukai lattice. So you have the exponential sequence. You take a tau homology and you use so alpha. So you have A2x OX star tau goes to into H 3
Are we singular cohomology now?
tau.
Talc homology with Z coefficients are not good.
Hmm?
You don't want to take talc homology with Z coefficients.
Analytic? Yeah. Yes, because I am on the complex number. So X 3Z, and then X 2X OX. And here something that I don't care. So alpha is here and is torsion. This is torsion free. So alpha comes from a B here, an element here called B field. So what happened? You can use this B field to create. Use B to define a Chern character from the Grothendieck group to the Q cohomology. And then you use these to you get an integral structure that I'm again swiping thing under the rug because so this is pages as pages in the hybrid stellari paper. So it's so this is the integral part. Of E to the V A star X cube. And what you have is that if you have derived equivalence, it induces a map. So alpha represented by a B field B, and Z is represented by a B field B prime. It induces a map B Y. Did I put?
You tried.
B prime. And the conjecture is that, so there is a natural orientation here. And the conjecture is that if you have a derived equivalence, you get something that preserves the orientation, and if you have something that preserves the orientation, it comes from an equivalence. And what Reinecke shows is that preserves the natural orientation. So it's like a positive. So, okay, so how did we do it?
Sorry, elementary question. Could you just say a word about what you mean by the natural orientation this has? What is
Because of these, you can break it in like 4 vectors, like in some vectors. It's and there are like some axes. Yeah.
Okay.
So it's really like you have to see how the structure of that is.
The hot structures?
Yes.
Yeah. Okay, I understand. Yeah. Okay.
Yeah, it's a
I
hot.
see. Yeah.
It's because there is a weight to Hodge structure.
Yeah. And you want to preserve some plane and
you want to preserve that.
Right.
So that is.
Yeah, I see.
Okay, so.
And you said that's to Reinecke? You said this is a result of Reinecke?
Yes. It started with his master thesis, if you want to get the present.
Sure, okay.
And in his master thesis, he didn't complete. He had some he had laid down, but he was using a different deformation argument because it was used what is Stellari. Hoibert-Mukai Stellari deformation argument using Toda. Toda result, the formation of derived category and Hodge's cohomology. But then when during his PhD, the first times of his PhD, he continued working on it, and he found out that with Max and Martin, it was much easier. So, but it's still technical, and the technical part I'm going to say something now. So the point is, it was known by Hoibert and Stellari we had that it was okay if dBx alpha has no spherical object. You can say, why? OX is a spherical object always. No, because we are twisting, so there is no OX. OX is not an object. in here. Or it is an object in here if this is trivial. So it was okay if this has no spherical object. So then we had like Lieblich provides a family of K3s X over some S was very general fiber has no so and also it lived alpha tilde. So the very general fiber dB x alpha prime has no circle. If you wonder, well, how can you deform Brouwer class without problem? The answer is yes. And for if you're really curious how one do, yes, if the characteristic, if the order is co-prime with the characteristic of the base field, but here it's 0, so we are really happy. Well, and well, if the characteristic field is 0 or the order co-prime, and there is a paper by Bragg on
characteristic P.
in characteristic P, in which he also studied the wild case in which alphas order in which that is terrible.
Terrible. YouTube's watching.
No, but the deformation it's fun.
Yeah, it's hard.
So the thing is, everything is super nice as soon as the Brouwer class is tame.
Yeah.
But if it becomes wild, then also the deformation problem becomes wild. Okay, so he finds this, and then this is not. Okay, we are almost there. So we have a lift. So the idea that we have a deformation, so the idea we can deform, but it's not really a deformation like in Max and Martin. What he does, he base change to a metal neighborhood of the central fiber. Or analytic neighborhood. Oh. And now this is exactly a family like we have discussed till now. And then we use Lieblich-Olsson to deform the equivalence and also use the fact that this property the property of being signed, like preserving the orientation, is locally constant. So it's if the central fiber is in some way, also the generic fiber is in this way. So and then then use fiber pencil line. Okay, seems easy. This part, it's hard. So again, you want to use Lieblich-Olsson, you pay by having a deformation problem in your hand, like you have to provide the right deformation. So this is the technical part.
Could I ask, is it Samuel projective history or it could be non-projective?
I don't know. I don't know. But I think it could be non-projective. So the gut feeling is I think it could be because Bragg and Lieblich to prove something about the finiteness of twisted partner of K3, they use this twisted line and they get to something that is
Even a characteristic P, I
yeah.
crazy, yeah.
And then yes, so and then the paper by the deformation argument of Lieblich-Olsson and Stellari, using Hodge homology, that was made because there was a problem on K3 that was easier on analytic K3, and so they deformed there, and then they solve it, and then they. Okay, so my time is really over, and
I think you're right on time because you started a little late, so we're right on time. Yeah.
Yeah, right on time, and so I will stop here.
Thank you.